Hi, I'm Yang Hao, and I'm going to present our work about scaling language image pre-training by masking. In this work, we propose a fast language image pre-training method, FLIP, which introduces the masking idea in CLIP to present a simple yet efficient CLIP training method. FLIP architecture has two encoders for images and text. In the image branch input, we randomly mask image patches with a high masking ratio. Then the model is trained using contrastive learning for image-text pairs. Our proposed FLIP method leads to a favorable trade-off between accuracy and training time. As shown in the right figure, FLIP improves both accuracy and speed over the non-masking CLIP baseline. The introduction of masking in FLIP brings two main benefits. First, in the same amount of training time, the model can see more pairs of samples. Second, with the same memory limit, FLIP can contrast more pairs of samples in larger batches, which is potentially beneficial for contrastive learning. Now let's look at some properties of FLIP from some ablation studies. This table shows the effects of different masking ratio. The entries here are under the similar memory constraint. As we can see, image masking yields higher or comparable accuracy and speeds up training. For example, with 50% masking ratio, it reduces half of the training time with the additional 1 point gain. This slide compares the results of different batch size. The masking idea of FLIP reduces the memory usage, thus enable larger batch size. As we can see from the table, a large batch has bigger gains over smaller batches. During inference, we use intact images without masking by default. It creates a distribution shift between training and inference due to masking. Thus, we add an unmasking tuning with very short schedule. As we can see, the tuning effectively reduces the distribution gap. Now let's see some FLIP results on standard evaluation tasks. This table compares the zero-shot ImageNet accuracy for FLIP with different CLIP variants, including CLIP from original paper and the public version OpenClip and our reproduced CLIP. As we can see, FLIP is better than both OpenClip and our reproduced CLIP, which are pre-trained on the same line dataset. We also evaluate different methods on linear probing and fine-tuning protocols on ImageNet. Similarly, FLIP outperforms OpenClip and CLIP counterparts pre-trained on the same line dataset. Here we can see FLIP also performs better on zero-shot image text retrieval tasks. Similarly, FLIP also achieves good results on image captioning and visual question answering tasks. We further explore the scaling behavior of CLIP, leveraging the speed-up gain from FLIP. Specifically, we study the scaling along the three axes, including model scaling, data scaling, and schedule scaling. As we can see, model scaling and data scaling consistently outperform the baseline on different evaluation tasks. Specifically, we find data scaling is favored for zero-shot transfer tasks, while model scaling is favored for transfer learning tasks. We further explore the benefits of joint scaling across multiple axes. As we can see, model and data scaling are highly complementary. Scaling both model and data together, we observe a substantial gain, which is even larger than the sum of individual gains from scaling them alone. Finally, joint scaling three axes together achieves the best results in most cases. which gives promising signals to further scale the vision language models. Thank you for your listening, and our code is already released in the above GitHub repo.